Okay. So, this is more or less going to be the last part. I mean, again, time permitting, I can cover some other attacks with, but I am changing gear now. So far we have seen web security, now I am going to talk about program security. Okay. So, remember I said that when you can compile programs, you can get root access. So, that is roughly what we are going to see now. Okay. So, this requires a little bit of operating systems background, and I have heard many of you have not done OS yet, right? Fine, I will explain whatever is needed for you to understand the. So, we are going to look again, buffer overflow attacks are again very popular attacks. These are often used to get root access. So, let us look at how things work. So, this is all background. If you know already, this is just going to reinforce what you know. You are aware that whatever code, let us say browser itself is some bunch of code, and when you run it, there is a process that runs, right. If I run Zoom, Zoom is a process that is running, browser is a process that is running. Okay. If I run some code like this, compile it and run, that is also a process that is running. Okay. So, whenever you run processes in an operating system, there is some memory that is assigned to that particular process, and this memory is virtual memory. Okay. So, you think of it as starting from 0 and going up to some particular point. And what I am showing here is the memory that is being allocated for this particular process or a program in this particular case. So, here for example, this is a program. Okay, this is a C program, and this program will be saved like this in the memory, and there are different parts to this. Again, let us see what each parts are. So, this text segment is where this code, whatever code, the binary of that code after compilation is what is sitting here in the text segment. So, basically these are program instructions, you go one by one and execute each instruction, that whatever it is telling. This data segment will save things that are static and global. So, for example, X will get saved here because it is static and global, whereas this BSS segment will stay programs that are defined within here. Okay. So, that is that Y will get saved here, and whenever as part of the program, if you are allocating memory through this malloc or whatever, that will get saved in the heap. So, this malloc whatever PTR will point to heap memory, and then there is a stack. This is where we are going to focus predominantly on. Other aspects you do not really need to know, but stack is something you need to know. This stack basically will save the variables associated with a given function. So, there is main function, main may in turn call some other function, let us say foo, foo may call some other function, let us say boo. So, basically foo variables will get saved in the stack, main also will get saved in the stack. So, this again I will show shortly the figure. So, here for example, as part of this main function I have defined A, B. So, they will get, and some pointer also I have defined, these will get saved in the stack, whereas the memory that the pointer is pointing to will get saved in the heap. So, the pointer variable is being saved in the stack, but the pointer is pointing to a bunch of memory that will get saved in the heap. Okay. So, that is effectively what this is telling. Okay. So, this is the background. So, I think the same thing that is repeated here for better clarity. So, I will get back to the previous thing. So, this as I said, let us focus on a stack. This again stack is very important to understand buffer overflow. So, in this case, as I said, there is a main function which is calling another function called f with 2 arguments, and then there is a printf. Okay. So, this stack will have this portion corresponding to the main stack. Again I am not getting into it, but let us focus on the f stack. So, this is the f stack. So, when main calls f, f stack will be pushed into that stack. So, it gets pushed into the stack, and here is what I want you to know, stack grows like this. This is the low address, this is the high address, the stack will grow like this. Okay. So, these arguments a, b, it is going to put in this memory. Okay. It will say a has a value 1 because you are calling it with value 1, a will have value 1 here, b will have value 2 here. And once you finish this function, you need to tell where to return to. So, once you finish this function, the printf will get called. So, that return address will go back to the text portion in that whatever I have shown earlier. It will tell what to execute next, which will go back to the text portion of it. And there is also something called a frame pointer. So, all this variables a, b, c, you need to know their memory location to know that b is what is it called, some bytes away from this memory location, and a is some bytes away from this memory location. So, the frame pointer, what it does is the CPU will note what the frame pointer value is. This is nothing but pointing to a memory, and relative to this frame pointer you can locate where a, b and other variables are. This point is clear. So, frame pointer is telling that, so when I am executing this stack, forget this previous frame pointer, when I execute this stack, the CPU will note down what the frame pointer for this is. How it finds out I will tell shortly, but it knows where the frame pointer is. Once it knows the frame pointer, it knows that a is at frame pointer plus 8 bytes, b is at frame pointer plus 12 bytes. It will know the location of where a, b are relative to the frame pointer. So, basically to access the arguments, it needs to know the absolute memory location, and others are relative to that. Okay. So, that is the purpose of the frame pointer. Now, what is this previous frame pointer is, once you exit the stack, and when you exit you are going to go back to the main stack, in which case you need to know again what the variables in main are. So, you have to save what the frame pointer corresponding to main is, so that once you execute you will now load the main frame pointer, and from that you can figure out where the variables in main are. Okay. So, that is precisely what is happening here. I mean, this may be a little bit challenging, but roughly if you get the attack, you do not really need to know too much detail, but you will understand the attack even if you do not understand most of these things. Okay. So, that is what is listed here, and then of course, in this there is an int x, so x is saved here. So, point is these are arguments. Apart from that, there are two fields called return address and frame pointer. What is more important for us is return address, which is telling where to execute the code next, and if there are other things like these will continue in this particular fashion. So, this is the function call stack. So, basically if main called foo, foo in turn called bar, the stacks are stuck in this particular fashion, and when you exit bar it will go back to the foo's. So, here you will choose foo's frame pointer and save. In foo you will save the main's frame pointer, so that you can access the variables corresponding to that particular stack. So, that is what this is telling. Okay. Now, we are coming to what this buffer overflow attack is. So, this is an example of a program which has a vulnerability which is called the buffer overflow. So, what is, let us see the program. So, there is some bad file, basically some file that is there in the computer, and you are opening that bad file. Okay. And what you are doing is you are reading 300 characters from that bad file, which you are storing in this string, and then you are calling this function foo with those string, which basically you are passing to the function foo 300 characters. That is what you are doing. Okay, so that is what it is happening here. Now let us see what foo is. This is what foo is and this is its corresponding stack. So again let us see, the argument for foo is a string. So that is why this is saved here. Then there is return address, then there is a previous frame pointer, and then you are defining this buffer. By the way, this should be 99. Okay, so you have a buffer 0 to 99. Okay. And then you are saying string copy whatever input to buffer. As you can see here, the string is 300 characters, whereas this buffer here you have only allocated 100 characters. Okay. So, this is clear. What until now what has happened is that from main you are copying some string which is 300 characters into foo into a buffer which has only 100 characters. So, naturally you can see what is going to happen when you do this copy. You are going to, when you do this buffer copy, you are now going to overwrite these addresses. In fact, you will overwrite further into whatever, how much ever it is there, you are going to overwrite. By the way, this is 99, not 11. Now, there are multiple things that can happen. So, when you overwrite, this return address is going to get overwritten, because as I said, you are copying 300 characters when the buffer has only space for 100 characters. So, something else will also get overwritten. When you overwrite the return address, bunch of things can happen. One is that this overwritten, whatever you are putting in here, it is a bunch of bits basically, whatever you are putting there. Now, because we are dealing with virtual addresses, that may not map to any physical address, in which case the program will crash. So, when you do this overwriting, if you write some random junk here which is not any physical address, the program will crash, because you are trying to access some address that is not there. It could be so that is case 1, where it is an invalid address, program will crash. The case 2 is where it is a valid address, but it is a protected address. Maybe it is kernel is writing something in that space where a user cannot access it. In this case also the program will crash with a protected address. And the third case is it may not be protected, but that address there is not an instruction. Remember, return address has to point to an instruction for it to execute. If it is not an instruction, if it is a data portion, then again the program will crash. Okay. And the last is what we are interested in, is that if it happened to be a valid address with program, then you will start executing that program. So, if somehow, if you saw whatever we have done, if in here you are able to overwrite to some memory location which is going to execute some malicious code, you can get what you want. So, the idea in buffer overflow is where you are getting some input from a user which you are overflowing the buffer because you did not do a proper check, and when you overflow you will write the return address such that it will return to some place which is within your malicious code and start executing that code. So, that is the basic idea of a buffer overflow. So, I will show this to you in this particular case. So, remember in the example we have seen, we are reading something from a bad file, and as part of the bad file there will be some portion which will have malicious code. So, this often will be the web shell, this will be the web shell script. Okay. So, this is also part of your input. So, bad file which that main is reading, you will have some malicious code, you will have this new address, and you will basically what you are doing is you are taking, so this corresponds to 0, and as I said this is only 100 bytes, but what you are reading is 300 bytes. So, you will take this and write like this, and this is what gets written in the stack. Okay. And when you overwrite it, this new address you will write it such that it will point to this particular portion, so that when it returns it will start executing from this point on. Okay. The basic idea is clear what buffer overflow is doing. Basically, you are not checking limits of a buffer and you are letting it copy something which the user is providing, and the user will provide this string that I am showing here, where there is malicious code, and this address will point to this malicious code is also residing on the stack. Okay. Typically, this is supposed to go back to that text portion and execute, but here you are saying go to this portion within the stack and start executing it. Okay. So, then you are going to do lot of damage, and these attacks are not that easy to launch because you need to get these two things correct. First is you need to find the address. When we say address, this is the absolute address. This is, you can't give some, I mean you can't give that this is relative to this way. You have to tell exactly the address of the malicious code so that it will return to that address and start executing. So, finding this address of the malicious code is not easy. You need to know exactly where that malicious code is. Okay. And similarly, constructing this bad input file, which I mentioned that should also often have a shell code, this is also not that easy to construct, again for reasons I'll mention shortly. So, so now let's see what is this, how do you find this address. When you are writing that bad file, you know the offset of the malicious code with respect to buffer, because you are constructing the bad file, you know that you are copying from this is something you are constructing. So, you know that if this were 0, this, because you are constructing, you know, you can tell maybe that is starting at the 150th byte. Okay. This you know, that relative position you know because you are constructing this file yourself. But as I mentioned, knowing this relative does not help. You need to know the absolute value, how things are saved in the stack, for which you need to know what the stack address is. Okay. So, that is the challenge there. But we do not know the address of the function foo stack frame. So, where exactly is the stack of foo frame starting, that we do not know. And it is not that whatever foo is going to print out the value of its frame pointer or anything, because that is not part of the code. So, you may not know that, but it is possible to guess this information, because if it is a 32 bit, you have 2 to the power of 32 address space. Of course, it is a huge address space, but our search thankfully is not very large. So, what often happens is that the operating system places the stack often at a fixed starting point. Okay, because this is how things were in the past. Now, it does not do that anymore, but in the past the stack where it starts is always fixed. You run the same thing again and again, you will see the same address. And if you do not have too much recursion or too many function calls like move, main calling foo, foo calling bar, bar calling something else, then the stack will keep growing. But if you have only one call, the stack is very small, as in it will just have only 2 frames in the stack. Okay. So, if it is not deep, then also you do not really need to. So, if you are somehow on the same machine and get a copy of the program, you can debug the program using the GDB debugger and then start figuring out where the stack is starting, where certain pointers are and so on. Accordingly, you can guess where the malicious code address is going to be. So, this is what one can potentially do. And there is another thing which you can do, which is called no-op sledding. Again, let me see what I mean by that. See, you need to be able to guess reasonably well, but it does not have to be exact. The reason for that is, suppose you guessed at this particular point and you put the return address which is mapping here, you can just put no ops there, and which no ops means there is no operation, it will ignore this and it will keep on doing this till it gets to this point, and from that point on it will start executing. So, there is some leeway by putting no ops in the below the malicious code, but if you jump somewhere here, then nothing can be done. Okay. So, it is important to put no ops here and the malicious code, but somewhere you have to jump within here so that the malicious code gets executed. Okay. So, that is the basic idea of the buffer overflow. So that is one aspect, which is how do you guess the correct. So those methods that I have said are help you in guessing the correct address. The other is you have to write a shell code. That is, in the bad input you have to write shell code, and this shell code has to be written in assembly language. And one of the bigger challenge there is this shell code cannot have this null character at all, and it is very difficult to write shell codes without null character, because the moment you see a null character, the buffer string copy will terminate the copy at that particular point. Okay? So you have to be able to write a shell code without the null character, which means you have to encode the shell code where null characters don't appear, which means then you have to decode itself first. So this is a little bit complicated. I don't want to get into too many details here, but this is a challenge. But there are people who have written the shell codes already for you. They are available in the internet. You just need to download it. Okay? So this is, for example, the malicious code, an example where you invoke the bin sh through this executive thing. So this is an example of the bad file. So what does one do to solve this particular problem of buffer overflow? So there are multiple approaches. One is that whenever you copy, don't blindly copy. You can use string n copy, where if you want to copy only 100 bytes, be explicit with you specifying n that you want to copy only 100 bytes. The most common approach which is used these days is what is called address space layout randomization. So what this does is, where the stack starts, each time the program runs, the operating system will assign a random value to the stack, thereby you cannot guess. Remember, all that return address the attack will launch only if the return address is guessable. Here, when the operating system will always start the stack at a random address, because you cannot guess, the attack will not succeed. So that is with respect to ASLR. There are also compiler side approaches. This is called stack guard. Again, let me show an example of this. So this is roughly showing, okay, let me cover this and then I will show. In this case, the address space randomization is disabled, and if you run the program 2 times, as you can see, it's the same value that you are seeing. Whereas here it is enabled, so if you can see, it is going to be random each time. Okay, here the stack is random but the heap is not, so that is this parameter. Okay, so based on this you can see that things are okay. So this is another compiler. The earlier was OS based defense, this is a compiler based defense. So what you do when you are compiling this code is you insert, the compiler will insert this as part of the code, where it will put guard, it will put some secret value, some, I mean this is not a variable, this is some string that it will put. Okay? And when you are returning, it will basically check whether whatever it has put matches this secret. So if you did buffer overflow, this guard would have been written with some junk, in which case when you are exiting, this guard will not match the secret. If there was no buffer overflow, the guard will match the secret. You understood what is happening here? So basically you are introducing one extra variable here and putting a fixed value there, which you know. If the buffer is not overflow, the value stays the same, then you will return properly from this. If the value has changed, that means some buffer overflow happened, and thereby you are going to exit the particular program itself. Okay, so that is how the stack guard works. So this is more or less with respect to the buffer overflow. It's a common security. Well, I have to tell one other aspect. So there are other, like we covered stack based, there are heap based also. And finally, how does this help you get root permissions? So far I have mentioned that you can get buffer overflow to execute malicious code, which is a shell script. But when you launch this program, If it is running with user level permissions, not root permissions, you will get a shell script with user access only. You won't get shell script with root access. But ideally, you want root access. Okay? So, oftentimes these buffer overflow are going to leverage what are called set UID programs. So, let me briefly talk about it. I will just spend 5-10 minutes talking about it. And these set UID programs are special programs. If this set UID program has a buffer overflow, you can get root access. So, let us see what these set UID programs are. So, in that context, let me tell in Linux is what I can cover this in. I hope you can relate to the Linux side of it. All of us want to change password, right? For that there is some my password, whatever command you execute, which will ask you for some password and you will enter your password. And this password that you type basically gets saved in a hash form in this file. This is a file. Okay? So, it is a shadow file which has a hash of all the passwords of the particular machine. And this password file, if you do ls-l, you will notice that it has read write permissions only the root will have. You as a user cannot write into this file. In fact, you cannot even read into this file. Only root can do that. But when you execute that password command to change your password, you need to be able to write into this file. But then you as a user do not have permissions to write into this file. So, how is it done? So, there are multiple approaches one can take. What the Linux operating system has done is that it will handle it through set UID. What set UID does is there are two aspects to set UID. So, there is something called any file has a user ID and it also has something called effective user ID. So, this file, the set UID programs are owned. I mean, they can be owned by anyone, but for us to launch the attack, they are owned by the root. So, for example, this password command that you are using is owned by the root. Okay? And it is a set UID program. So, what happens is when you execute other programs which are not set UID programs, the user ID will be the same as effective user ID. Whereas, for set UID programs, the effective user ID will be the owner of the file, and if the owner happens to be root, the effective user ID will be root, whereas this user ID will be whoever is running the program. Okay, so I hope this distinction is clear. So, there is a program, the owner of this program can be root, but I as a regular user can also run the program. When I run the program, the user ID will be mine, okay, Chebrolu, whereas the effective user ID will be the root because the root is the owner of that particular file. So, when you do ls-l for these set UID programs, you basically will see something like RWS and you may see something or RX, something like that you may see, which basically tells that this user or you may see something like this. So, this is anyone else other than root, they cannot read that file. Whereas, because it is a set UID program, what happens is when you are executing the program, the privilege gets changed to the root. That way it will take your password as input and write into the file. But the moment you exit the program, again the privilege gets downgraded. Okay? So, the way Linux handles is you can execute the program, but when the program is executing, it will change the effective user ID to root, which means the program has access as a root, thereby it can access the shadow file and write. But because the programs are very carefully written, I mean the program is already there, you can't alter that program, and it will only do take your input password and write into it. It won't do anything else. So you have root access only to do that task. You don't have root access for anything else. That is why it is okay to give root permission to the program, because you know that the program is supposed to do only that. Okay, so the context of the setuid programs is that if the setuid program has a buffer overflow and you are executing that buffer overflow program, and when you are executing that malicious code can run as root, in which case you will get a root shell, and that is how escalations happen. So it is not that you randomly choose any program that is out there and you won't get root shell, you will get only user shell. But if you really want root shell, you have to target so-called setuid programs. Only then you will get root shell. And there are some setuid programs with these vulnerabilities, and that is where people have launched attacks. Okay. So that is it with respect to this buffer overflow. Probably we have some extra time, but I can just take some questions. I don't want to start another topic. Yeah. Canaries, yeah. Yeah, the guard is acting as a canary, yeah. It is a number. That is what I meant, is the code is written like that, but this secret is basically a number that you are putting. No questions? Okay, fine, thanks.